So chapter 6 is really titled Thermochemistry. What does thermo mean? Heat, right? I said it's about heat. Thermochemistry deals with heat within reactions. So if heat is being released or if heat is being brought in. We're going to look at an experiment called a calorimeter experiment. Have you heard of that? Have you heard that word before? Calorimeters are experiments, and then we try to trap the heat inside and see where the energy transfer takes place, all that kind of stuff. So that's going to be the experiment we hope to get to in this chapter, but we don't have all the things we need to have, so I'm making the things we need to have. So we're going to try to get there. It might be a basic experiment, but we're going to try to get there. So in this chapter, we need to start with energy, right? Because heat is, at its basis, a form of energy, okay? So anything that has energy has the capacity to do what we call work, okay? If you were in physics with me, you know that work has a different meaning scientifically than what we usually think of as work, right? But if something contains energy, that means it has the capacity to be able to do work on an object, to change its energy levels, or it has the capacity to produce heat, okay? So the law of conservation of energy is listed here. It should be something we're pretty familiar with. Would we agree? Law of conservation of energy. It's got one tagline here at the end: cannot be created or destroyed. Right? That's the important part of the conservation of energy law. Energy can be converted from one form to another, but can be neither created or destroyed. Where else did we hear this law of conservation with? We have the law of conservation of energy and then law of conservation of matter or mass. Mass cannot be created or destroyed. And so those are things are considered to be conserved or constant. Okay? Since energy can't come from nothing or go to nothing, that means the amount of energy in the entire universe is constant. Right? But only thing that happens is that energy is transferred. Right? It's transferred, it's transformed from one thing to another. Right? If we need energy for ourselves to function, what do?
Eat.
We eat, right? What we eat becomes energy, right? Our body goes through different processes to come up with that energy. So it's not coming from nothing. It's being transferred from the sun to the plant to the animal to the whatever it is that we eat that now becomes energy. Right? So it's just a big transfer. But the total energy in the universe is considered constant, or conserved is another word, right? Conservation of energy. Okay. We need to deal with two different terms here, endothermic and exothermic. Have you heard those before? Yeah, good. Endothermic means that we are heat that's flowing into the system. Okay, we are absorbing energy from the surroundings. Okay, so if something is endothermic, we are having heat flow into the system. If we're exothermic, that means heat is flowing out of the system, so the surroundings are becoming warmer. Okay, two kind of main parts to chemical reactions, the system and the surroundings. So if we gain energy as a surrounding, then that means that energy had to come from somewhere, which means it came from the system. So the terms system and surroundings, you'll see them used here at the beginning pretty often, but the system is what we're looking at. The surroundings is anything around it, right? It's pretty simple definition. But if we lose energy in our system, it has to be gained by the surroundings. If our system gains energy, that means the system must lose energy. No, I said that wrong. If we gain energy in our system, our surroundings must be losing energy. All right. Is freezing an endothermic or exothermic? Even though I just gave it to you. What is it? Exothermic. Okay, after I already put that out there. Can you explain to me why? It is leaving the water, right? Exo means energy. We said exo means energy is what? Flowing out of the system. So when something is freezing, the system, whatever is becoming frozen, is energy is leaving that system and going toward its surroundings. So that's considered exothermic. Okay. I don't know I think I added that to the previous slide here. We're going to classify each of these things as endo or exothermic. I just want you to write it to the side of your slide. or whatever. I'm going to pull up the answers here in just a second. But let's talk through each of these. Your hand is the one that's underlined. So that's what we're paying attention to. That's the system. If my hand gets cold when I touch ice, is that endo or exothermic? Exo, right? My hand is becoming colder, which means heat is leaving my system. And where is that heat going? To the ice. In terms, what's happening to the ice? It's melting, which means this, if ice was underlined, it would be endothermic, right? Because heat would be entering that system. Okay, the ice the ice gets warmer when you touch it. Just one step ahead of myself. Okay, so that would be considered endo. Sorry about that. Okay, water boils in a kettle being heated on a stove. Endo or exo? Endo. Heat flows into the water to speed up the particles and make them move and then make them boil. Water vapor condenses on a cold pipe. Endothermic or exo? Exothermic. As something condenses, that means it goes from gas to liquid. That's what condenses mean. So gas to liquid means it's cooling down, which means it's leaving the system. And then ice cream melts. Endo or exothermic? Endo. Endo because it's getting warmer, heating up. Feeling good about those two terms and their relationships? Okay, good. All right. So we said this whole unit is called thermochemistry. So we're going to start looking at thermodynamics and the laws of thermodynamics. Any of the study of heat and its reactions and all of its stuff is called thermodynamics. Okay? Like there's whole classes you could take on thermodynamics and chemistry, right? That was a class I had to take in college. Specifically a whole class over this chapter. So it's a big, broad topic that we're going to cover just a teensy bit of. Okay? When we talk about the law of conservation of energy, it's a lot of times called the first law of thermodynamics. And that all that means is that we can't create or destroy energy. Okay? The first law of thermodynamics. Believe it or not, there's a zeroth law of thermodynamics they added later that they thought was most important. And it's called the zeroth law, but I don't have that up here. All right. This is the equation for, what do you think? Energy. Any idea about what these variables would mean? We haven't seen them yet before.
Work.
Okay, good. W is work, and Q is heat. Oh, I didn't put that on there. Okay. Q is considered the variable for heat or even energy. It's kind of in there twice. I don't know. And then work is the W. All of these have the unit joules. Okay, capital J is joules. And sometimes you'll see it measured in kilojoules. That's fine too. Okay, they mean two different things, but as long as they're consistent along your equation, you should be good to go. Okay, so joules or kilojoules. All right, when we talk about thermodynamic quantities, we have to have two different parts to the quantity. It's kind of like when we deal with vectors that have to have a magnitude and a direction. This is the same type of thing. This quantity has to have the magnitude or the number, and it also has to have the sign that indicates the flow of energy. Are we gaining energy or are we losing energy? And so the sign of it is really, really important, meaning that if we've got a positive energy situation, we need to make sure we have the plus, and then the negative obviously has to include the negative. So usually if something's positive, we just leave the plus sign off. But these ones, it's kind of important that we include that positive sign to tell us it's positive. Okay? Heat is given with the variable Q. I told you that on the last one, sorry. Okay? So in these energy systems, when we're talking about the signs and the energy flow, here's how we look at it. If it's an endothermic process and we have heat going into the system, our Q value is positive. If we have heat leaving the system or an exothermic process, our Q is negative. I would go ahead and highlight that, like circle it something, because that's something you're going to have to refer to pretty often is the signage of these values, because they won't always be given to you in the problem. Okay? We had energy equals heat plus the work done. And so to get work, you can do this kind of simple calculation here, pressure times the change in volume. Okay? Change in volume. pretty simple equation. I don't know if I had it on there for you to write down or not. These are two things I added since I printed your notes, something that you need to have. It doesn't mathematically exactly work out this way, but if we have a volume expansion, our work value needs to be negative, and if we have a volume compression, our work value needs to be positive. Okay? It's not something that mathematically proves true, because if I have a volume expansion, my final volume is going to be greater than my initial volume, which would give me a positive work value. Does that make sense? So you have to add it in there. I'm not going to really go into the derivation of the equation as to why that's the case. You're just going to have to just believe me, okay? Because I don't want to go through that. But the work that's associated with the expansion of a volume under certain amounts of pressure is negative, and then the compression of it is a positive value for work. And that's going to come up once in your homework today, so I wanted to point it out. Okay? Let's see. Sorry. All right, last couple of things here I want to cover. If the system is doing work on the surroundings, if we have an exothermic type of reaction, our work is negative. If the surroundings do work on the system, then we have an endothermic reaction, which is a positive value for work. So these are the other parts of that kind of, I don't know, I thought a little note card you could make or something, the little clues I gave you for the W values and the Q values, positive, negative. If you want to spend some time after class or just make yourself a little note card for it, I think that would be helpful. It's not something we're going to use a whole lot. Tomorrow's chapter or tomorrow's unit, I think, is much more important than today's, but we have to get through this one today to get there. But those values will come up in our homework today, knowing whether things are positive or negative. Okay? Let's try one here. Calculate the work associated with the expansion of a gas from 46 liters to 64 liters at a pressure of 15 atmospheres. Okay, so this is using the equation that we just had up a little bit ago. Work equals pressure times change in volume. And we said, right, we talked about the expansion or compression. So since our volume is expanding, my work value is going to end up what? It's going to end up negative. So I'm just going to go ahead and put the negative in there so I don't forget. Right? This is just from that little rule I gave you. If it's expanding, my work value is going to be negative. So I want to plug that in so I don't forget it in my answer. All right, then I go pressure is 15. Change in volume. So what's my change in always supposed to be? What minus what? Final minus initial. So my final volume is 64 minus 46. So I'm going to do that math, or you're going to do that math. That's the change in is 18. Okay. $18 times my pressure. 270. Thank you. And so now my work comes out at negative 270